one of the fundamentals of generative AI is autoencoders. So we talked about density functions earlier. Let's talk about autoencoders. These are a really key concept in generative AI. And so there's this idea of encoding information. So let's take the example of a text-to-text model. So this is like the ChatGPT experience. We provide text to the model. It encodes that text, and then it gets encoded into something called a latent space. And then there's a decoder that takes that latent space information, converts it into new text that then, in this example that I'm giving, ChatGPT provides text back out to us. So encoding text, latent space representation, decoding. I think altogether, this describes an autoencoder. So maybe fill us in a bit more on what these terms mean and what important role they play in generative AI systems.
Yeah, cool. Great question. I'll take it back actually to an example with images because I think it's slightly easier to sort of visualize for your listeners. So let's imagine we've got an image and it's in it's 1024 pixels. So high dimensional space. Every single one of those pixels has 3 color channels. So you've got a lot of numbers basically that describe that picture. And as we previously mentioned, there is some density function that describes why that image is very likely to be a true image and other noisy images aren't. Now, what autoencoders look to do is say, can we map this high dimensional space of the image domain to a latent space, what is known as a latent space of a lower dimension? So you could even map to a latent space of 2 dimensions. Then it's very, very easy to visualize. You're just imagining a plane, and then on that plane, there are mountains and valleys, and that determines whether some of those points in the latent space are likely to be generated and some aren't. Now, the reason why this is useful is because it forces the model to make generalizations over the pixel space so that it can compress that information into the latent space. It's a bit like if someone said to you, I always give the example of cookie jars or biscuit tins, which are cylindrical. How many numbers do you need to describe the shape of that biscuit tin? The answer is 2. You need to know the height and you need to know the diameter of the cross-sectional circle. If you know those 2 numbers, you could reproduce the biscuit tin. So even though this thing exists in 3 dimensions and you could view it from different angles and come up with different pixel pictures of it, actually you can describe it using 2. And in that latent space, you could basically move around it to produce different kinds of cylinder. And the same thing, exactly the same thing is true with models like diffusion models or even variation autoencoders. You're basically saying to the model, find me a low dimensional latent space where if I choose any point within that latent space over some distribution, like a normal distribution centered on the origin, I am pretty likely to find something that is truly a real image. And then, so what the decoder is trying to do is move back from the latent space to the pixel space. Can you take these 2 numbers and recreate the biscuit tin? So if you join those 2 things together, you've got what's known as an autoencoder, because it's trying to effectively compress the information down to something small and then expand it back out again to the original image. It's auto-encoding itself.
Nice. Great explanation. I love that 3-dimensional biscuit tin cylinder represented in 2 dimensions. That's such a crisp way of describing how this latent space can contain information like that. Awesome. So there are different kinds of autoencoders. We've got variational ones, for example, which are more popular today. So how do variational encoders differ from traditional ones? What unique capabilities do they offer?
Yeah, so the problem with vanilla, let's call them vanilla autoencoders, so not variational, is there's a few problems, first of all. If you just let the model map to any old latent space, like you just say, take the pixel space and I just want you to find 2 numbers that kind of represent what that image is so that you can decode it. The problem is it's very hard to sample from that 2-dimensional space because, okay, so let's say the point 100, 100. Is that a valid image? What about 200, 200? Like 2 million, 2 million? Where in this still pretty vast space should I be sampling? And so what you end up with is a very difficult latent space, firstly, to sample from without much structure. It's got no incentive to kind of pull similar concepts together because ultimately it's unconstrained. What a variational autoencoder does is it makes a very slight change to the loss function. And it effectively says you've got to include a term which makes sure that the points, when you map them into this latent space, are as close to a standard normal distribution as possible. By a standard normal distribution, what I mean is a normal distribution with a mean of 0 and a covariance or standard deviation of 1. So we know how to sample from this object. It's really common, and we know exactly how it works. And by doing that, what happens is, first of all, everything gets compressed to something that looks like a normal distribution. And that helps us in two ways. First of all, it means that there is a degree of continuity in the latent space. So you can move around it and be pretty sure that anything within this normal distribution is going to be something that's likely to be a real image. And if you move to the extremes, then you're going to find something that's less likely. But we understand what this distribution means. So we can sample from it really easily and just make sure that if we're choosing random points from a normal distribution, standard normal, that we're going to be able to decode these points to a real looking image. So it's a bit like the glue. The variational autoencoder is a bit like the glue that glues everything together and makes it a true generational model that we can sample from, and not just this abstract autoencoder object, which it's not very easy to work with, basically.
Nice. Great explanation. Crystal clear. So variational autoencoders, they allow us to constrain distributions to standard normal, which leads to better behavior in the autoencoder. We get better results.
Precisely, yeah. And the term in the loss function to do that is called the KL divergence, Kullback-Leibler divergence. And it's the glue that makes it the first kind of generative model I would recommend everyone starts with.
I see that KL divergence. That's big in information theory, right?
Yeah, it's a way of measuring the difference between two distributions. So like if you've got your distribution of points and you want to compare it to the standard normal, you could use the KL divergence to do that. The beautiful thing about this is that it's actually got a closed form solution for a standard normal, which means that you don't actually need to do any sampling to work out what this value is. You can just write down the answer, which is super powerful.